All right, so good job on the homework. That was partially a refresher and partially a chance to try turning in the homework in the way I specified. So as far as the engineering, right, we had a 5-volt source. We had a 2 kilo ohm resistor and a 3 kilo ohm resistor, and they were sitting in a loop. And so it asked you to find an equivalent circuit with a single resistor, and everybody correctly knew that series resistors can be added. So your equivalent circuit looks like this: 5 volts, 5 kilo ohms. And then you're asked to find the current coming out of the voltage source, and this is Ohm's law. So the voltage across here will be 5 volts, and Ohm's law says V equals I times R. So 5 volts is the voltage. I is unknown. We're trying to find the current, but the resistance is 5,000. And it's useful to convert to just bare units, so volts, amps, ohms. If you're not comfortable with metric prefixes, so volts, amps, and ohms. So I'll say 5,000 ohms. So you solve that equation for I, and it's 5 over 5,000, which is 0.001 amps, which you can then convert to 1 milliamp if you like, or you can leave it as 0.001. And then it asks, since that's the current coming out of the 5-volt source, what's the current across each of these resistors? And current is constant around a loop. So the current across each of these resistors is also 1 milliamp, or 0.001 amps. And now you want to find the voltage across each of these, and it's still Ohm's law, V equals I times R. The voltage is what we're trying to find. We know the current is 0.001 amps, and the resistance of this resistor is 2,000 ohms. And if you multiply that out, you get 2 volts. And then if you do that here with the 3,000, you'll get 3 volts. And that should feel kind of warm and fuzzy, because 2 volts plus 3 volts is 5 volts. That's what you got coming out of your battery. Yeah?
My question was, when you find a voltage drop, do you just take the total voltage and subtract it by the voltage going through the resistor?
You can do that, although you didn't need to do that here.
I was wondering.
So, but yes, if we know that there's 5 volts from here to here, and we know there's 2 volts from here to here, we can subtract and say it's 3 volts from here to here. But if we were going to talk about that, I would approach it a little differently. There's specific ways I try to build up to that in 120. Basically, if you go around, if you go into the positive side of a voltage, you can add it. If you go into the negative, you subtract, and it should all come out to 0. That's the short version of KVL. So, so the 2 issues I saw here were, one, being confused about what you're solving for and what you know. If we're trying to find the voltage across here, we don't know what V is, right? We know what the current is. That's what we did in the earlier parts. And we know what the resistance is because we're told the resistance. If you know 2 out of V, I, and R, you can solve for the third. Either V equals IR, I equals V divided by R, or R equals V divided by I. The other thing was units, and units are just tricky sometimes. So I threw a K in here, so this is thousands. If you just convert to bare ohms, volts, amps, you're less likely to go wrong. A few people came up with some megavolts coming across the resistors, which logically doesn't make sense, right? With a simple circuit, meaning it's only got wires, resistors, and voltage sources, if you got a 5-volt battery, you can't get, 5,000 volts or 2,000 volts or 3 million volts coming across these resistors. It just doesn't make logical sense unless you have transformers or other non-simple elements like that. So, so you can sort of sanity check your numbers like that. So homework looked good. A few homeworks where the edges were kind of like jagged, which which I'm going to ask you again to try to make sure the edges are clean. If you pull it out of a notebook and it's got a perforated edge, fold it over, peel it off carefully, right? The jagged edges tend to catch other pages, and people's homework can get eaten, or if something gets stuck to it, I pull a paper out and another one goes flying, and it's just, it seems like a silly thing, but it's a whole lot easier logistically if the edges are all nice and clean. But the style of the homework, the presentation, the headers, the numbering, all that, perfect. Really, really nice job. So, so that makes my job a whole lot easier to do as far as making sure everything gets graded, and if there's partial credit issues, I can follow what you're doing, and that looked great. So nice job on that. All right, so any questions or comments on the homework? And you're working on homework 2, right? And that's some binary BCD hex stuff. Oh, okay. Can you turn it in on Thursday?
Is that due Thursday?
Homework's due Thursday, right? Yeah.
That's a long time.
Yeah, it's a week.
Right.
I'm less likely to lose it if it comes in. That's all. Okay, good. How did lab 1 work out? I got 16 lab reports, so if you didn't turn in a lab report, turn it in as soon as possible. If you get it in like before this class ends, I'll count it on time. If you forgot to turn it in or something. So let's run through the lab. So experiment 1 was looking at the equipment, drawing some pictures of them, showing a usage example, and there's not a whole lot I can go through on this. I'll look at what you did for that and make some comments if anything's relevant, but that's kind of a sort of self-explanatory. Experiments 2, 3, and 4, so you were hooking up a function generator to an oscilloscope. Oscilloscope lets you look at a waveform that's changing in time. Function generator generates signals that change in time, so these go together nicely. So what did you notice, if anything, peculiar as far as differences between experiments 2, 3, and 4?
Kind of seemed like 4 couldn't keep up.
Yeah.
It was like, it got really weird and stretched.
Yeah, so the ideal square wave is this, although drawn better than I'm doing right now. Right? And the practical square wave that you look at on the oscilloscope probably looks pretty close to this. Sometimes it may have a little funniness in spots, but depending on how closely you look at it, but it pretty much looks like a square wave. But that experiment 4 tended to look a little more like this maybe. And that's exactly what's going on. The function generator can't actually produce things at this frequency. The oscilloscope can handle megahertz. Okay, it can display pretty accurately what's coming in, so this is probably a function generator issue. And it needs to, drive the voltage up to 5 volts and then pull it down to ground to 0 volts back and forth really fast, and it's having a hard time doing that.
I wasn't sure exactly what I meant by ideal square wave, so when I Googled it, the best resource that I could come up with was people talking about how it can't be an instantaneous drop and lift.
Mm-hmm.
And so I did cite my source on that, but I wasn't sure exactly what it meant by ideal. So I assumed the little curly curls is what you meant by how does it differ from an ideal square wave, but I'm not sure.
Yeah, no, exactly. And if you were to look at this, so there's all kinds of things you can do with the oscilloscope, and I can show you in lab sometime if you like. You can blow up different sections of it, and you can make it so that the distance from here to here is a few nanoseconds. Okay, a few billionths of a second, and that really lets you see what's going on. If you're toggling, 100 times a second, and you're showing one square wave, this is about 100th of a second. Okay, you can do much finer resolution than that. And if you were to do that, you might see that your waveform actually looks like this. This would be much longer. But the way it's actually going up is not instantaneous, as you said, from 0 to 5 volts. it actually has to go up smoothly. Because it's a real-world device, and most things don't change instantaneously in the universe. They move continuously, so the voltage actually goes from 0 to 0.1 to 0.2 to 2.5 to 3 to 4, up to 5 volts. And when it gets to 5, it doesn't just suddenly stop climbing, it's going to slow down, and so we get this little curve there, or we get maybe an overshoot, and then it comes down. And so yeah, those are the non-ideal parts of physical generation. And then the high frequency one just looks all wrong because it's struggling to keep up. And to certain degrees we have to deal with, or we can ignore these realities. In digital circuits, a lot of times we can ignore these realities. That's part of what digital means, is that we don't care that this is ringing a little bit up here at the top or jittering around down here, right? This is a 1, this is a 0. This is a 1, this is a 0. We sort of sweep all those details under the rug and just say it's above 3 volts, it's a 1. It's below 1 volt, it's a 0. That's one reason people will say things like digital is much more exact. Or if you're selling digital headphones, you'll say these are more precise because they're digital, right? They're really not, but that's the sense in which we say that. There's less uncontrolled error. Okay, so experiment 5, I glanced at a few of the labs, doesn't look like there's any issues there, right? So you know how the protoboard works from 120, so that's a rehash of that. So let's dig into the traffic light, because this is going to come up in most of the labs this quarter. So three-way intersection, red and green light on each one, single lane, and we were supposed to sketch the intersection, identify variables, and develop a truth table. So the truth table is the main takeaway from this. So let's draw the intersection. And there's going to be 3 lights. So there's a few ways to do this. Let me draw a green west and a red west, a green south and a red south, a green east and a red east. And those are the lights that'll be displayed. And we also want sensors to tell us if there is a car present. So here's a sensor west, here's a sensor south, here's a sensor east. And I'm just going to call this west, south, and east, because we're going to make equations out of them. So single letters are nice. So here's a system diagram. So we have west, south, and east. And we have outputs, green west, red west, green south, red south, green east, red east. And I'm going to indicate what 1s and 0s mean for this. So a 1 means there's a car present. 0 means there's no car present. So those are the sensors under the road that you hope notices your car is there. And these are the lights, and I have 6 outputs going to the 6 lights, 2 on each lane. And so 1, the light is on, 0, the light is off. There's another way to do this that we'll look at in a second. But let's make a truth table for this. So we have 3 inputs. And we have 6 outputs. So green west, green south, green east, red west, red south, red east. So if there's a car on the east, that's got priority. Anytime there's a car on the east, that lane is going to get a green light, and all the other lights are going to be red. So, so for any of these cases where we have an eastern car, east is going to be green, and everything else is going to be off. And I'll fill in the reds. Well, we'll fill in the reds now. So that's red, red, and the red is off on the east. All right, if there's no car on the east, but there's a car to the south, south gets priority. So if there's a south but nothing on the east, then south is going to have a green light, and everyone else will be red. And same thing up here. And if there's only a car on the west, that's this row right here, then west gets a green light. And everyone else is red. And if there's no cars, you can decide what you want to do. You could make everything red, or you could give west priority since west hardly ever gets priority. Or you could, you know, take bids from local businesses and see which light you want to turn green. It's up to you. So I'm just going to make everything red if there's no one around. So there's a truth table that would work for this, with this first row possibly being different. Okay, there's a totally different way that we could do this, and this is completely valid for this lab. So there's your sensors. Again, 1 is a car, 0 is no car, but we can have just 3 lights. We can just say green west, green south, green east. And the meaning of this output is 1 means the light is green, 0 means the light will be red. So same behavior, but we're specifying 3 outputs, and you need some circuitry that says if I've got a 1, I should light the green light, if I've got a 0, I should light the red light. And if you do that, your truth table looks exactly like this. Because anytime there's a 0, that is supposed to make the red light turn on. So you can get away with this for the first few versions of this. Eventually we have to actually draw in all 6 outputs, because eventually we're going to have yellow lights also. And so we're going to have 9 outputs. But for first version, either a truth table will work fine. Does that make sense? All right, so one other comment. I'll look at the labs. I'll try to get them graded up in the next 2 days so you can have them back by Thursday. When I go through the labs, they're submitted as PDFs, so I'll go through and I'll make notes on the PDFs. Now, if you get 100%, you may still have some notes. There may be things that I didn't take off points for, but things that I wanted you to notice. So once the grades are entered, go through your lab report and look for any comments, okay? And it may just be, you know, this is awesome, this is beautiful, or it may be, you know, make sure that you put units on this equation or something like that. But if you lose points, you should always find in your lab where those points were taken off. And I'll say something like, you know, you forgot to include the outputs, -2, and there's 2 points. And any points that I take off, there should be something in the lab report that indicates the deduction. Those deductions should add up to whatever points were taken off a perfect score. So make sure you go through the annotated lab reports once grades are in. And it's really important because the first time that you turn in your lab, I may say something like, you know, you need to include a description of the experiment. But I won't take off points for it because it was the first lab. Second lab, if you make the same mistake, I'll take off points, right? So if you see the comments in the first one, you can ask about it. You can do it on the second lab, save your points. Make sense? All right, so one comment I'm going to make, because I've already seen it in a few times, is make sure that any figures that you put in, pictures you take or scans, make sure they're legible to the reader. Okay, take your PDF and look at it and forget that you're the one who put that picture in, right? And just look at it, make sure it's legible. Can you read the words that are written there, the numbers, and so on and so forth? And if not, then you need to blow it up or take a sharper picture or something. I can help you figure out ways to do that if you like. So I'll make comments about that as I grade through. Okay, let's look at lab 2. And then we're going to go back to working with logic. We're going to work more with De Morgan's theorem. I'll tell you some cool consequences of that. And we're going to work our way, probably by the end of today, to coming up with what we call K-maps, a way to simplify equations, which will help you as you're building circuits, because a simpler equation is usually easier to build. And by Thursday, we're going to start talking about product of sums, the flip side of sum of products. So a different way to write an equation from a truth table. Okay, so let's look at lab 2. So lab 2, you've got a bunch of different experiments going on. The first thing you're going to do is you're going to find these 3 unknown chips. They look like regular chips, but they've got a little masking tape or whiteout on the top, so you can't read a part number from them. So they're mysterious chips. And you're going to build a circuit to analyze this chip and then try to figure out what the chip is. So for the first chip, it's labeled unknown IC number 1. This is the circuit you're going to build. Okay. Pin 7 goes to ground, pin 14 goes to VCC. VCC means 5 volts in this course. It's always the power supply going into a chip. So VCC is 5 volts, GND is ground, that's 0 volts. And this diagram shows input A, pin 1, going to this switch that can flip between here and here. We don't actually have those kinds of switches in our parts box. So forget about all of this stuff over here. All you're going to do is take a wire out of pin 1. You're either going to connect it to ground, or you're going to have a 1K resistor connected to VCC, and you're going to connect this wire to the other side of that resistor. So instead of a mechanical switch, right, we're just going to take this wire, we're either going to plug it into this point, or we're going to plug it into this point, which is ground. If you plug it in here, that's a logic 1. If you plug it in ground, it's a logic 0. And then we also have a wire coming out of pin 2 on the unknown chip, and you can plug that either into power or ground, logic 1 or 0.
Are you gonna like change the picture so we don't get confused later on? Because we might accidentally put a switch in if we're gonna.
So all the other switches we're going to use are going to be switches that we can actually build. But this is sort of a visualization of a switch, but it's really, what this picture is saying is that this point can go either here or here. Well, you're just going to do that manually. You're going to connect, this is going to be one point on your proto board, this will be another, and you can connect it either there or there. And then other switches in the future, we'll talk about how to actually implement those. So we can put a 1 or a 0 into input A and input B. There's 4 combinations. You're going to build yourself a truth table. Show all the possible combinations of input A and input B, and for each one, take a look at this output coming out of pin 3. See if it's a logic 1 or a 0. How do you do that? You can use a multimeter and measure the voltage. And if it's a logic 1, it'll be around 5 volts, logic 0 around 0.
Can we use LED?
Or you can use an LED. So if you want to venture into LED land, right, get yourself an LED, a 1K resistor, make sure the LED is in the right direction, because you've got to go in the right side and come out the other side, and it'll light up if it's a 1 and go dark if it's a 0. So a good chance to practice with LEDs, or use a multimeter. Okay, so using those switches, develop a truth table for unknown IC number 1. And then take a look at component specifications for different kinds of chips and try to figure out what this chip is. So let me show you where you can find components. So if you go to linux.engrcs.com, this is a newer version of the engrcs.com website. Come down under Resources, Component Specifications. Here's all the different components that we have in our parts boxes. So 74LS00 is a 2-input NAND gate, and if you open that up, here's a truth table for it. So make your truth table by doing experimentation and then make a theory. I think this is a such and such gate. Come in here, find that gate, look at its truth table, see if it matches. Yeah?
Are most gates listed instead of 1s and 0s, is it H and L, high and low?
It really varies from sheet to sheet.
Okay.
But H will mean 1, L will mean 0.
Sure.
2 out of 2 are using H and L. Let's try this one. Okay, 3 out of 3, so maybe.
Just to know which one would be more preferred. Okay.
So I prefer 1s and 0s,
Okay.
but HL is also correct. All right, so that's your first experiment, okay? And again, make sure that your lab report is describing what you're doing. Don't just put down a truth table, right? You got to say we built a circuit, put in a picture of the circuit. If you take it from the report, put an annotation on there, say taken from lab report 2, etc., right? And we took the wire from pin 1, we connected to 5 volts, and we took the wire from pin 2 and connected to 5 volts, etc., right? And put in enough detail so somebody understands what you're doing, but you don't have to totally hold someone's hand, right? If you describe exactly what you did to put in a 0, 0 and what you did to put in a 0, 1, you can probably say we did the same thing to put in 1, 0 and then to put in 1, 1, right? So assume that the person reading your report knows nothing about lab 2, but they understand engineering, okay? So you don't have to teach them what a wire is or what a voltage is, okay? But the stuff that you're doing has to be explained. All right, experiment 2, exactly the same thing, but you use unknown IC number 2, and this time your inputs go to pins 4 and 5, your output comes from pin 6. Experiment 3, same thing, unknown chip number 3, inputs on 1 and 3, output on pin 4.
Should this all be on the same circuit board?
They can. You can put them all on one circuit board, or you can do one chip and then take it out and do the next chip and so on. It's up to you. That could be me. It's not. All right, clear on those 3? All right, experiment 4, we get to do some Ohm's Law. So this is what we touched on in the homework 1. And the hardest part about this is making sure that you're reading all the words correctly. The actual work is pretty straightforward. Measure the voltage across the resistor, calculate the current through the resistor. So you're building a circuit with a 5 volt supply, a 1K resistor, the other end going to ground. So you're actually going to build something like this. And then what does it want you to do? Measure the voltage across the resistor, calculate the current through the resistor. So you take your multimeter, and you put a red probe here, black probe here, you put it on voltage setting, and you measure the voltage. And it should say 5 volts, right? Okay, and then, so that goes in your lab. We built the circuit, there's a picture of the circuit. We measured the voltage across this resistor with a multimeter. The voltage we measured was 4.92 volts. Okay, then we calculated the current through the resistor. How did we do that? We used Ohm's Law. V equals IR, 4.92 equals I times 1,000. I equals 4.92 milliamps. Again, somebody wants to reproduce your work, so they've got to know, where did this 4.92 volts come from? Did you calculate that? Was that given to you? No, you measured it. How about the milliamps? Well, we calculated that using Ohm's Law.
Should we take pictures of like the photo board that we actually build?
I don't mind pictures. Izad takes off points for pictures, I think. I don't mind pictures, but they don't take the place of a picture, a circuit diagram. Right? So if it's a cool looking proto board or you got a million wires and you're really happy with it, I don't mind if you throw in a picture. But it's purely extra, right? You still got to have this, because this is something that you can actually build from. All right, so part B, you modify the circuit by adding another 1K resistor in series. And what does it say here? Measure the voltage across one of the resistors and calculate the current through the resistors. So pick a resistor, multimeter, measure the voltage, and then use Ohm's Law, calculate what the current is. Part C, same thing but 3 resistors. Measure the voltage across one resistor, calculate the current through the resistors. And then part D is a thought experiment. Imagine that you did this for n resistors, 1017 or 5 or some other number, right? Don't actually build it, but imagine that you did the same thing but you had n resistors in series. What do you think the voltage would be across one resistor, and what do you think the current would be through the resistor? So you're trying to generalize what you've done, and this looks more like the homework problem, except instead of 2 resistors you've got n, where n is just some unknown number. and you're looking for a formula. So that if I say N is 17, I can plug 17 into your formula and it says the voltage is equal to this. And I can plug it into your other formula and it says the current is equal to that. Okay? And you can check that formula because now if you plug in N equals 1, you should get the voltage and current from part A. And if you plug in N equals 2, you should get the voltage and current from part B. And if you plug in N equals 3, you should get the voltage and current from part C. So you can tell if your formula is right. You can tell if it's wrong if it doesn't match pretty close to what you actually measured and calculated in those first 3 parts. Is that clear? It takes longer to explain it than to actually do it. Right? So once you start hooking these things up, it's a pretty straightforward procedure to just keep adding more resistors. Okay, and then part 2, exactly the same thing, but parallel resistors. And here it's asking you to measure the voltage across the resistor and calculate the current through one of the resistors. Okay, so you're going to measure the voltage with the multimeter, and then you're going to use Ohm's Law. You know what the voltage is, you know what the resistance is, you can find what the current is. And then part D, come up with a general formula if you have N resistors in parallel. And the biggest mistake people make is they just kind of like guess what the answer should be, and they're not always intuitively clear what the answer should be. And I always mention in 120, the first time that I did this and I started grading the homework, I'm like, wrong, wrong, wrong. And I got to like the 6th paper and everyone was getting the answers wrong, and I'm like, wait a minute. So I went back and checked, I had the answers wrong. Right? So it's really easy to switch something around here. So think about it. All right, and then we come back to the traffic control signal. So we're going to continue to develop the circuit for the traffic light. So same setup as before, truth table, but you're also going to include a logic design. So once you have the truth table, we started talking about how to turn that into equations. Right? We did that in 120. We reviewed that on Thursday, and we're going to continue developing that idea today and next class. So you're going to come up with equations, and once you have an equation, you can make a circuit. And we looked at a nice way to have inputs going up and down and come across into your AND gates and OR those together. The trick is, I'm going to be specific about how you need to make these logic diagrams. So let's say you want to do something like this. Simplified circuit. So we've got 2 inputs, A and B, and we've got an output X. And you make your truth table and you simplify it and you come up with the equation X equals A ANDed with B bar. Okay, so if you want to build this circuit, we need to take B, put it through an inverter, take that in A, put it through an AND gate, that's X. Okay, here's what you got to do. So this is what we're after. So logically, we need an inverter. So come down to the component specifications, look for an inverter. There's a 74LS04 hex inverter. And you gotta go down a bit for the truth table. So there's the truth table. Input is on A, output is on Y. And the output's just the opposite of the input. Okay, look at the pins for this. And we're using a 74LS04. That's this. So this is the wiring diagram. If we were using a 5404, it would be something different. So this is the wiring diagram. It's got 6 inverters. 1, 2, 3, 4, 5, 6. And for each of these, the input goes on A, the output goes on Y. So for example, if we feed into pin 1, we can read the inverted output on pin 2. If we feed into pin 12, sorry, if we feed into pin 13, we can read the output on pin 12. Well, we only need one inverter, so we can pick any of these 6, but we got to choose which one we're going to use. So I'm just going to say, let's go in on pin 1 and come out on pin 2. So over here, I'm going to put a little 1 right here to indicate pin 1 and a 2 here to indicate pin 2. And I need to tell whoever is building this that this should be a 74 LS04. Now I could write 74 LS04 down here, but I'm not going to. I'm going to label this with a U followed by just a 1. So U is kind of the symbol we use for chips. And the first chip's going to be U1, second chip will be U2, and so on. And then up here in the upper right corner, I'm going to have a block called a component ID block. So you probably saw this somewhat in 120. So what goes in the ID block? Well, here's the component ID. So this is going to be U1. And here's the part. It's a 74 LS04. And up here, I'm going to specify what pin do I connect to ground and what pin do I connect to power VCC. So go back to your data sheet. Ground is pin 7, VCC is pin 14. So I'm going to put that in here. Ground is 7, VCC is 14. And sometimes we also put down an entry that says no connection to tell us which pin should not be connected to anything. So I'm going to use pins 1 and 2. I'm not going to use 3, 4, 5, 6. I'm not going to use anything on the right except for VCC. So I'm going to list no connection for 3 through 6 and 8 through 13. So 3 through 6, 8 through 13, no connection. Now if I have another inverter in my circuit, I could draw that, I could label it U1, I could put down which pins on U1 I'm using for that second inverter, and it's still the same physical device. Right? And up to 6 inverters I can take from this one part. If I have a 7th inverter, I might label it U2, put in the new 74 LS04, and go from there. Okay, so there's B going in. Let's take A and put it in, and this has got to get ANDed with the output of that inverter, and the output of that is X. Okay, so this is a 2-input AND gate. Yes?
If we use the same inverter, would you then want us to change the no connection?
So then you change the no connection, yeah, take out the ones that you use. So usually fill this in at the end. Okay, we need a 2-input AND gate. So go back to your component list, 2-input AND, that's a 74 LS08. And the pin out looks like this. We can go in on pins 1 and 2 and out on pin 3. Or we could go in 4 and 5 and come out on 6. Power is still pin 14, ground is pin 7. So an AND is a 74 LS08. I'm going to call this U2. U2 is going to be 74 LS08. Ground on 7, VCC on 14. And I'm just going to go in on pins 1 and 2 and come out on pin 3. And so I have no connection on 4 through 6 and 8 through 13. And then down here in the lower right, this is your project ID block. And you can put all kinds of different stuff in here. You can put in your name, you can put in a project ID, you can put in a date, and any other information that you find useful. This one's less formal than the component ID block. But you can also have a place for a signature saying this is approved. And after you build a circuit and you test it and you know that this diagram is correct, you can sign off on that. Or later on, if it says have an instructor review your design before you build it, right, you can present that design to an instructor, they can say that's good, and then the instructor can sign off on there. So these are things you would typically see in, a work environment, but it's good practice to get into these. So why do we do all of this? Why do we put down pin numbers and part numbers and no connection and all that kind of stuff?
Someone else can reproduce it?
Say again?
So someone else can reproduce it?
So someone else can reproduce it. Right, that's the first thing, because this is science. So somebody can take our lab report and they can build exactly the same circuit that we built, and they can follow the procedure, and they can look at their observations and compare it to your observations and confirm or refute what you saw. The second thing is you're designing the circuit, right, which requires an understanding of Boolean logic and eventually state machines and things like that. That's different from building the circuit. If you have this piece of paper, you can build the circuit without knowing anything about what the circuit does. You see a U1 74LS04, you go to the parts bin, you find a chip in there, and you take it out and you put it in your proto board. And you connect pin 7 to ground, 14 to VCC. You connect pin 1 to whatever B is. You connect pin 2 to pin 2 on U2. Well, U2, you find that part, put it in your board, hook up ground and power, connect pin 2 to pin 2, pin 1 to A, pin 3 to X, and you're done. So you can take this and you can hand it to somebody else whose job is to build the circuit, right? Or you can hand it to a computer. You have to put it in a different format, obviously, inside a computer, but you can take something like this, feed it into a computer, and something that'll automatically pick parts out of a bin and connect wires together and solder them and give you a board back that implements your circuit. Right, so this is the full specification of the circuit. The other reason we do this is for debugging. So when you finish your circuit and you put your switches in and the light's supposed to light up and nothing happens, you can use this to debug your circuit. And basically, you put your switches in a position where you're expecting X to be 5 volts, for example, and you measure it and X is 0 volts. Okay, so what's wrong? Well, first of all, I can go directly to my board and I can figure out where X is being generated from. It's pin 3 on this chip. So now I take a voltage reading at pin 3. If it's 5 volts, I've got a problem in my wire between pin 3 and whatever X is. If I'm reading 0 volts, okay, this is an AND gate. I'm expecting both of these inputs to be 1. Obviously, either one of them is 0 or the AND gate is defective. So measure your voltage here at pin 1 and here at pin 2. If both of those are 1 and the output is a 0, this is not an AND gate. So what's wrong? Maybe it's the wrong chip. So you double check the ID. Oh, I got a 74LS18, not an 08. Okay. Or you didn't power it up, so double check the power connections. Or maybe it's defective. So everything looks good, you just grab another chip, plug it in. If it starts working, that's great. If not, you got something really weird going on. Okay, but chances are you expect both of these inputs to be 1. One of them is going to be a 0. Okay, let's say this is a 0 instead of a 1. Well, that's a problem. Where is it coming from? Pin 2 of this chip, measure the voltage there. If the voltage right here is 5 volts and the voltage here is 0 volts, you got a wiring problem. So trace your wire from here to here, and it's probably plugged into the wrong spot. If this is 0 volts and it should be 5 volts, there's a problem with the inversion, so check the input. If this voltage is correct, then again, maybe it's a problem with the inverter. Maybe it's the wrong chip, maybe it's a bad chip. If this is an incorrect voltage going in, follow it back to where it comes from. So you can debug from an output that is incorrect, you can work your way backward and pin down exactly where the problem is. And it's really easy to do with this kind of diagram. But you got to know pin numbers, you got to know part numbers, and so on and so forth. All right, does that all make sense? Okay, so that's the kind of diagram that I'd like you to do for this Part C logic diagram, using only those parts listed on the course website. So that's this collection of parts, because these are the parts that are available to us.
Are you going to make the website on Canvas?
No, it might be on there, but so the general course, the general engineering website is just engrcs.com, and you definitely want to know that site. That's where all the syllabi are, all the books, and so on and so forth. And the modern version is just Linux, engrcs.com. So it's probably somewhere on the Canvas page. All right, I'll check it at the break, which is coming up right now. All right, so any other questions about Lab 2? So that's due in a week, started early, and bring questions on Thursday. All right, let's do a 5-minute break. I'll put a link up to that website on Canvas, and then we'll start playing with some more logic.